Hello, my name is Avilas Zareka. My roll number is MAB 18033. So, the first question goes: a hydraulic turbine is designed to produce 26.845 megawatt at 95 rpm under 1526-29 of head laboratory facility. Laboratory facilities are available to produce 4572 feet of um, and to absorb 37.285 kilowatt from the model turbine. Determine the appropriate model test speed and scale ratio and volume flow rate assuming a model efficiency of 86%. So from the given data we know the left side is of the prototype and the right side is of the model. So P1 is a power. So P1 is the power of the prototype. P1 is the power of the prototype that is given 26.845 megawatt. That is, we convert it to kilowatt, it becomes 26.845 into 10 to the power 3 kilowatt. And N is the speed of the turbine. That is a 95. That is 95%, 95 of RPM. And H1 is a head that goes 15.24 feet. So the right side data that is given as the model data that is given. The power is 37.285 kilowatt, and the RPM is not given, and we have to find the RPM, and the head is 44572 feet. That is converted into meter and 1393 meter. Um, so for speed um, uh, we have to calculate RPM. So for speed by we we equate the dimensionless specific speed of turbine equation. So it goes as um, k equal to n1 p1. N1 is the rpm of the prototype. So the n1, so the formula goes, and n2 is our rpm of the uh, model. So the formula goes n1 p1 1 by 2 by rho half of g, that is the acceleration, gravitational acceleration, and h the head loss, h1 by 5 by 4, 5 by 4, equal to n2 by n2 p2 half by rho half of g h2 5 by 4. So the n2 becomes p1 by p2 and half, that is by half by h2 by h2 by h1 5 by 4. So we calculate equate and substitute a value, and we get the answer is 56565.965 rpm. 565.965 rpm. So now for the scale ratio, by applying the dimensionless uh, uh, dimensionless power coefficient, we have to calculate the scale ratio, that is d2 by d1. So the formula here goes p1 by rho n1 cube d1 5 equal to p2 by rho n2 cube d2 5, n2 cube d2 5. So by using and substituting the values, we get d2 by d1 equal to 0.092. Now using similarly, by using the hydro by equating the hydraulic efficiency, um, we use the formula p2 by rho q2 gh2. We calculate and equate the values, and we get the answer to be 3.173 meters cube per second. That is, we need to find the efficiency eta. So the second question goes as condition at the inlet to the nozzle of a Pelton wheel are P equal to 48.2633 bar and V equal to 24.64 kilometer per hour. The jet diameter is D equal to 19.05 centimeter and the nozzle coefficient is K nozzle equal to 0.04. The wheel efficiency eta H equal to 0.86. Calculate A the power output, B the normal operating speed, and C the approximate runaway speed, and D the torque at zero speed. So here I have drawn the diagram of the nozzle, and this is the here I have drawn the diagram of the nozzle, where this is the outlet. This is the outlet of the uh, V1, and this is the inlet. And from by applying the Bernoulli's equation, from the Bernoulli's equation, we get P1 P1 by rho z plus V1 square by 2z equal to V2 square, V2 square by 2z plus K V2 square by 2z, where K K is the friction coefficient, and uh, by applying substituting the values, we get the V2 equal to 96.45 meter per second. Now we know that the power flow discharge velocity. Now the flow discharge, we applying the by applying the flow discharge formula, we get now applying the flow discharge formula, pi by 4 d square into v2, pi by square d square into v2, where q equal to area into velocity, area into velocity sorry the net head H equal to P1 by rho z plus P1 square by 2z. Now, by applying the formula of the net head, we get 494.76 meter. We know that the output power P equal to rho q z h by eta h, the efficiency eta, and we get the power, calculate the and substituting and calculating the value, we get the power to be 1139 megawatt. Now we have to find a normal operating speed. We know that the maximum efficiency, that is we know that the maximum efficiency u by v2, now we know that the maximum efficiency u by v2 equal is 0.46, that is given. So we calculate and we get the value to be 44.36 meter per second. And applying the value of velocity normal direction u equal to pi n d by 60, and we get the rpm to be normal rpm to be 347.39 rpm. uh, and again then we go on to calculate a runway speed in the maximum unsafe speed of the petrol. After this maximum speed, the turbine may break down. The turbine speed of this turbine may break down. So now putting the value of maximum runway speed, that is nr equal to 16 to 96.45 by 3.14 into 2.44, we get the rpm to be 7553 rpm. So we get the rpm to 7553 rpm. Then we find that T ideal PQR V2 minus U 1 minus cos theta, by applying the formula of the torque at normal operating speed, we get the T to be torque to be 292.851 into 10 to the power 3 nm Newton meter. While when the speed is at 0, that is U equal to 0, T equal to 0.6 into 10 to the power, applying the formula, and we get the torque at 0 equal to 542.245 into 10 to the power 3 nm. So here the next question goes: the reaction turbine at the Niagara Falls are of the Francis type. The impeller outside diameter is 4.5 meter. Each turbine produces 54 megawatt at 107 rpm with 93 8.8% efficiency under 65 meter of net head. Calculate the specific speed of the turbine. Evaluate the volume flow rate through each turbine. Estimate the penstock size if it is 400 meter long and the net made of 83% of the gross head. Assume the suitable data if necessary. So here it is given. So here it is given D. The capital D equal to 4.5 meter. That is the outside diameter, and the N, that is the speed, is 107 rpm. That is 1.783 rpm. So we convert the megawatt to watt. It is 54.10 to the 6, and the H is the head, that is 65 meter. Mm, so applying the formula, and that is we get the speed of the rpm 134.72 rpm. So now the volume uh, flow rate ratio, that is Q, um, is 90.28 meter cube per second. We apply the formula and we get this value. So now the penstock, the penstock size net head equal to H equal to 0.33 H naught. H naught we get 78.314 meter. So that is the head gross equal to head net plus head friction, and we get a head friction as 13.312. So FL Q square equal to 12 by 12 D5 equal to 13.312, and we get the value of the D, that is 3.8962 meter. Using the Moody's chart and assuming a penstock is made from the concrete, we get the epsilon by D naught equal to 0.015, and taking the Reynolds number, that is 3 into 10 to the power 5, we get F equal to 0.04. So, in this question, we need to find out the hydraulic so in this question, we know that the formula of the hydraulic efficiency, that is V, uh, and is given in the diagram. So and nu H equal to VW1 minus VW1 by V1 by GH, where the nu is the efficiency and uh, VW is the relative velocity between the water and the blade, and V1 is the velocity of water, and G is the acceleration due to gravity. So we put the formula and we get applying the formula and substituting, and we get the value to be 5.26 meter per second. And then in the propeller turbine, that is the input velocity is equal to output velocity. uh, we assume we assume in the overall efficiency in rpm, overall efficiency is we get is a safe power nu equal to safe power by water power. uh, Now we calculate safe power water power, and we get 250,000, and the Q to be 127.55 meter cube per second. So now the Q, we applied a formula, and we get when we get Q equal to we have to calculate now VF2. So we get the value to be 9.99 meter per second. So from equation 1, we get 10 phi equal to 9.99 by 35.34, and the phi becomes 15.74 degree. That is a runner whereas angle at the outlet. So again the tan theta, we have to uh, get the tan theta value. So we get it to be 0.33 and the theta to be 18.2. So that is the value of the inlet runner value angle of the inlet. So that is all. Thank you, sir.